Okay, just so YouTube Nation understands, yesterday we had a slight interruption. Our desks are sitting close together. Anna, are you going to lose the finger? Okay, you had your hand on the side of the desk. Larry moved closer. Oh, wow. That was rather forward. And we definitely had blood, did we not? We had blood. Uh, who came to the rescue? Bailey Barber. Because I am now first aid certified and I can now be a head coach in the state of Minnesota, I applied the Band-Aid. And we're good to go. So, exciting days in calculus. You never know when you might lose a finger. All right. She's exactly. Well, no. She's got signs all around her room now that say protect your fingers. It's like she's getting bored. I don't. You guys ever seen The Shining, where he goes stir crazy in the cabin? That's her in April. Okay, it's what happens. It's like, look out! Yes, tomorrow's my day to raise morale, and it starts with my sister's birthday tomorrow. So shout out to Elise. Elise right now is in the Dominican Republic, laying on the beach. Oh, she's going to be 37. 37. Bring you treats. Oh, Elise, they think I should bring you treats because it's your birthday for the class. Unbelievable. Oh, to raise morale. It was never your guys' idea to raise morale as B-Nels. You support it? That's stupid. All right. We're going to do something different today, okay? We're going to make just a slight change. Let's see what happens, okay? Shh. Find the volume of the area bounded by y equals x squared, x equals 0, and y equals 4. Shh. Rotated around the y-axis. This is the key part. When you see rotated around the y-axis, things change. So I was working with a few people about making sure that you generate the appropriate graph. Let's make sure that we can get the appropriate graph to start with. What does y equals x squared look like? Parabola? And x equals 0 is a... Right, but I'm cutting it off because it's the x-axis, so I'm also bounding it here. And then the line y equals 4, what's that? All right. So now we're going to take this and we are going to rotate it around the y-axis. So I'm going to get the same shape. Spinning it like this. Oh, you like the disc there? All right. So if you were going to slice this, how would you slice it? I mean, like, so Bailey, what'd you show me? Do it again. You can slice it like that. The idea is when I slice it, I got to get the same type of shapes all the time. You wouldn't want to slice it like that, would you? Because whatever shape we get, we wouldn't know the area of it. But if we slice it like this, then we're going to get this kind of shape. So that's my shape I have to work with. Well, I know that this is x equals 0 in the middle. The radius is right here. Oh boy. Okay, so when we slice, you can see that the same thing applies. You would do the top function minus the bottom function, or the right minus left. In this situation, the outer portion is generated by the function y equals x squared. However, we are not going to be working with respect to x right now, because we're rotating it around the y-axis, and remember, if our rectangles were stacked vertically on top of each other, okay, that means we integrate vertically. As we stack all of these discs on top of each other, we're going to start at the top, right here, and we're going to go to the bottom. So, are those, as I integrate vertically, are those x values or y values? Y values. I start all the way up here at y equals 4, and I go all the way down to y equals 0. So that means that your radius is going to have to be in terms of y. We're integrating with respect to y. So all I did was I took y equals x squared, and I changed that to x is equal to the square root of y by simply square rooting both sides. So the distance from the center to out here is equal to the square root of y. For example, okay, let's just look at this. All right, what number would you square to get 4? You would square 2. You can see that this has a coordinate right here of 2, 4. So the question is, how far out am I? Well, you're 2 units, whatever the square root of y was. So you can see square root of y gives you that 2. All right, so you can see how that works. So now I have this shape. Now I need to be able to find the area of the top portion. What's the area? Area is equal to pi r squared. So area is equal to? My radius is the root of y. So area is pi y. And what is the thickness of this disk? dy. Look, does it have horizontal thickness or does it have vertical thickness? Vertical. So therefore, you can look at your slice right away and realize it has vertical thickness. So therefore, it's dy. So all these indications tell us that we're working with y. So that is my well, my area, excuse me, was pi dy. So the volume of this piece was, pi y dy. And now we're going to integrate it. So I'm going to have pi y dy. And what are my bounds? From 0 to 4. Oh, that's a piece of cake. More like a ham, though, isn't it? Cake. All right, so what's the antiderivative of y? Y squared over 2. And we got to multiply that by pi, and we're going to evaluate it from 4 to 0. The 0 goes away. What's 4 squared over 2? 8 pi. That's the same problem we did yesterday. The only difference is, instead of revolving around the x-axis, we revolved it around the y-axis. Okay, that was it. In that situation, yes. Let's look at a more difficult example. Find the volume, the area between y equals x to the third, x equals 0, and x plus y equals 2, rotated about the y-axis. I like to start with the line, x plus y equals 2. What are the x and y intercepts of that line? Two and cover up the x. What's y? 2. Cover up the y. What's x? 2. So the x and y intercepts are 2 and 2. So I could graph that line quite easily. If you can't graph using x-intercepts, then you can go ahead and put it in slope-intercept form, which would be y equals negative x plus 2. And you're going to get this line like that. All right, and then we have this beast, y equals x to the third. We know what that looks like, right? Starts down here, just like that. So, and then we have the vertical line x equals 0, which is the y-axis. So would everybody agree I have this shape right here? Okay, and we're going to spin it which way? Around the y-axis. Oh boy. How do you like that? All right, there's a problem. There is a problem. It's very good, very good. Do you see it? As I integrate on my way down here, I get, as I cut it, as I slice it, I'm definitely going to get a disc, right? However, what measures to the outside, the radius, changes at this spot, doesn't it? So we got to set up 2. Yeah, well, that 2 different functions generate the outside portion. Like right now, the outside is generated by x plus 2. What am I doing? X plus y equals 2. And then here, the outside is generated by y equals x to the third. Now, really quick, the thickness is the thickness dx or dy? dy. It's a vertical thickness because we sliced it the way we did. So therefore, everything has to be written in terms of y. Very good. So, so I've got this center, which in both cases is x equals 0. So I need an x equals equation over here. So what is the x equals equation right here? X equals, sure, 2 minus y. I like that better. Sorry. Freedom of choice, America. And then this one, I would have x equals cubed root of y. Very good. But now I have to set up my bounds, right? So these bounds. What do you think? How do you know 1? We would have to find the intersection of those 2 pieces, right? We would have to find where y equals x to the third and x plus y equals 2, where those meet. We could simply use substitution, put an x to the third in for the y, and we would get x plus x to the third is equal to 2. That's a third degree polynomial, right? We could solve those. X to the third plus x minus 2 equals 0. We don't factor third degree polynomials in that way, but we can always use the handy dandy. Starts with an R, rhymes with ational. Root's theorem. Very good. And we have a very good guess. Brooke came up with a guess. What's a good guess? 1. Let's try. If you plug in 1, do you get an answer? Yes. So we know that 1 is a solution. Okay? 1 is a solution. So therefore, we can say that the intersection point here is, in fact, happens at 1, 1. This spot up here is 0, 2. And this spot down here is 0, 0. So let's set up our integral. The integral, I'm going to work with the top piece, namely the cone shape deal. What is the top part of my bound? 2 to 1. And we are going to integrate. Oh boy. We got to figure out an area of this guy yet. We haven't done that. Area is equal to pi times your radius squared. So pi times this thing squared. 4 minus 4y plus y squared dy. And we're going to add that to then our other integral, which is, now we've got to, again, do area equals pi r squared. We have pi times, what happens if you square the cube root of y? Y to the 2/3, we'll just write it like that, y to the 2/3 dy. And what are my bounds? Very good. For the sake of time, can we just leave that? Knowing that we know how to do, we've been doing definite integrals for a long time, haven't we? You guys know how to do the definite integral, right? Setting it up is the key. So, good question. Your right is this function, x plus y equals 2. Your left is simply the line x equals 0. So if you do right minus left, you just get the function. As long as our center is 0, you don't come up with anything other than the function itself. Yes? Well, so I'm going to start by integrating this portion. Okay? I'm going to have a bunch of circles there. You can see I'm going to start up here at 2, and 1 is my changing spot. 1 is the spot where it changes, where this is my outside function that's creating the edge of the radius. And then it switches to where this becomes the outside function, where it is my radius. So that happens at a y value of 1. Start at a y value of 2, and then at 1 it switches all the way down to 0. Yes? No? Somebody else had a question over here. Okay. Alright, one more. Okay. We're going to leave, we're just going to leave that alone because I know that we can evaluate definite integrals. Question is, can we set up the integral appropriately? Last one, find the volume of the area bounded by the curves x equals y squared plus 5y minus 4 and x equals 0 rotated around the y-axis. What does that shape look like? Close. Sideways, headed to the left. Very good. So a great way to find the shape of a parabola is to find its intercepts. Instead of finding x-intercepts here, we're going to find y-intercepts. So we set it equal to 0, and I can factor out a negative. I get y squared minus 5y plus 4. 0 equals negative. How's that factor? Y minus 4, y minus 1. So I have solutions at 4 and 1. And again, you guys said this is going to head which direction? It's going to head to the left. So 1, 2, 3, 4. So that's my shape. And it's bounded by the curve, and then it says x equals 0. Everybody agree that that's the area that I'm going to be rotating? Okay. So I'm going to spin that. That was horrible. And so when we slice it, will we slice it? How are we going to slice it? So like this. Yeah, exactly. So when we slice it, we get, you know, those kind of shapes out of it. No, if you sliced it vertically, it's difficult to see, but you're not going to get a circular shape necessarily. If you slice it like this, if you slice it like that, instead of getting, you know, what's a nice circle, you're actually going to get a, kind of a nasty ellipse type shape. It's going to be difficult to find the area. Okay. Tomorrow will be a full work day practicing various volume type problems. We'll finish that one off. I didn't realize we were up against the bell here. Tomorrow, full day of practicing these type of problems, okay? Don't worry about any homework. Get caught up on where you're at. Tomorrow, lots of practice. Lots of practice.